Hi, today I'm going to show you how to prove this question. It's from Extension to Cambridge textbook. It's about how to prove Taylor series. So what is Taylor series? Taylor series is about proving the EX is equal to a series. So what series is? I'll write down for you. So it's proving EX is equals to 1 plus x squared on 2 factorial plus x cubed on 3 factorial and keep going like this pattern. Or sometimes we write it into limit when n approach to infinity and keep the same patterns. 1 plus x squared on 2 factorial plus x cubed on 3 factorial and keep going until get xn over n factorial but n approach infinity. So these are how they donated in here as the EX. Here, EX. You can see, yeah. So that's the same as this, or yeah, in the end the question E here, we're proving EX equals to capital EX. So that's the questions. So we're proving that EX equals to capital EX as they donated in here. So how do we prove this? So they have some lead up questions, question A, B, C, and then D, E. So the questions is actually separated into two parts. One part is A, B, C. We prove EX actually is bigger than capital EX, not equal to, bigger than or equal to. And then starting from question D, we actually prove that equals to, and that's how we prove in the end. So ABC is inequality. So let's start to proving that, okay. So let's do the question. So first question, let's prove A. So they give you e to the power of t bigger than equal to 1 when t is between 0 and x, which when x is bigger than 0, bigger than equal to 0. E to the power of t is bigger than equal to 1, as you can see on the diagram. So we're starting from here, e to the power of t bigger than equal to 1 with the t is in between 0 and the x. So, and then we start to integration on both sides to proving EX bigger than equal to 1 plus x. So integration both sides from 0 to tx. So e to the power of t respect to t dt bigger than equal to integration 0 to x 1 dt. So that gives us e to the power of t with limits 0 to x is bigger than equals to t limits 0 to x. So they give you e to the power of x minus e to the power of 0 bigger than equal to x minus 0. So which gives us ex bigger than equal to x plus 1. So that's we proved question A. And the question B, from we got the results here. If we integration one more time, so we can prove EX bigger than equal to 1 plus x plus half x squared. So let's do the B. So we have ET bigger than equal to 1 plus t for t is less than x bigger than equals to 0. So we integration both sides again from 0 to x, et dt bigger than equal to 0 to x, 1 plus t dt. So when we integration, we get a et 0 to x bigger than equals to t plus t squared on 2, 0 to x. And then we have ex minus e to the power of 0, which is 1. So bigger than equals to x plus x squared on 2. And the minus 0, which is gone. So we prove EX is bigger than equal to 1 plus x squared on 2. Pretty good. So that's question B. And the question C is continue to integrating in the similar fashions to proving EX is bigger than that. So I just do one more from there. I show you how to do the question C. So one more. So from ET is bigger than equals to 1 plus t squared on 2. We integration both sides. We get 0 to x et dt bigger than equal to integration 0 to x 1 plus t squared on 2 dt. So then we integration, the left hand side just become ex minus 1 again, bigger than equals, the other side would be 1 plus, no 1, x, we're not subbing the value of x plus x squared on 2, then plus x cubed on 3 times 2, which is same as 3 factorial. And the 2 we can write in 2 factorial. So we're starting getting the patterns now. So we get ex is bigger than equals to 1 plus x squared on 2 factorial plus x cubed on 3 factorial. So if we keep going, of course, we're going to getting next, the ex will be bigger than equal to 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial plus ... Keep going until the next one can get plus x power n with n factorial. So this is the question C. They ask you to prove bigger than that. When the n is approach infinity, if we keep going, then we can have n approach infinity. So with the x has to be bigger than equal to 0. That's the condition we have here. Okay, so that's question C. So pretty much we got ex is bigger than equals to ex, capital Ex, for x bigger than equal to 0. But the Taylor series doesn't have this condition for x bigger than equal to 0. Taylor series is for the x can be all real values. So we have to look at the left-hand side when x less than 0. But when x less than 0, you can see on the drawing, the exponential function, the value is less than 1. So we don't have the et bigger than 1 when the t is less than 0. So then if this one doesn't exist, everything we prove from A, B, C doesn't exist. So there might be less than, or maybe some parts bigger than. So they actually doesn't work for when x less than 0. So then how do we prove in the Taylor series for all values of x? Doesn't matter x positive or negative. And also another thing is we don't want to prove ex bigger than equals to capital Ex. We want Ex equal to capital Ex, equal to, not bigger than. So we're going to totally forget about A, B, C, and then we're starting doing the D with the new fresh mind. So they say by consider function e negative x times ex to prove it, the derivative equal to 0 for all real value of x, for all real values, not for x bigger than 0. So let's starting do the hx. E negative x times ex. So let's do question D. So they ask you to proving this new function, they call it hx, equal to e negative x times the capital Ex. So what does that mean? Means hx is equal to e negative x with the capital Ex is this, is the 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial, keep going forever like this. Okay, so that's hx, and we want to prove in the h dash x equals to 0. So let's do a derivative. So we have to use in product rule for the derivative. So u dash will be negative e negative x with the same thing here, x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial, keep going. And we have to plus with the u times v dash. So v dash, one derivative will become 0, x derivative become 1. So become 1 plus x squared on 2 factorial derivative become x. X cubed on 3 factorial derivative become x squared on 2 factorial. X4 on 4 factorial derivative becomes x cubic on 3 factorial. And then keep going like that. And then we factorize the e negative x outside. So we're getting -1, negative x squared on 2 factorial, negative x cubed on 3 factorial. Keep going, they're all negative. And then we plus 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus dot dot dot. So you can see that in the brackets here, that close brackets here, the two parts, they exactly the same and one negative, one positive. So they cancel out. So once they cancel out, then the answer just become equals to e negative x times 0, which equal to 0. So then we prove the D. So these are very important results. What is the function derivative consistent equal to 0 means? Means the function actually equals to a constant. So since the h derivative equal to 0, therefore the function hx equals to a constant. Then what is a constant? We're going to find out. Constant means no matter what value of x, the function value is always the same. So we just found the one value of x. Let's find out what is the h0. H0 means we put it in h0 means this. Okay, we e to the power of -0 with 1 plus 0 plus all the way they all 0. Right, that's the h0, which equals to e to the power of -0, which just equals to 1. So means h0 equal to 1. So which means the hx is always equals to 1. It's a very important result. Now we have hx equals to 1. So what does that mean? Meaning e to the power of -x with 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial, keep going, that actually equals to 1. So from here we can say therefore e negative x, therefore we can say changing that, we can say 1 plus x squared on 2 factorial plus x cubed on 3 factorial plus x4 on 4 factorial, keep going, that actually equal to e positive x times e negative x on both sides, getting positive x. Isn't that that's the proving of the Taylor series? So then we can say therefore the ex is equal to that, which is Taylor series. That's done.